So let's get started reviewing this part B2 and part C of the June 2016 Chemistry Regents. Let me remind everyone that on the bottom of the video there where it says show more, click on that. You'll see that I have links to every question on this part 2. So if you want to go directly to that question and not see the entire video, you can just click to the exact question you want me to review with you. So in any case, we are dealing with what I call the free response section, okay, the part where we have to add answers. And I will say this, many people are intimidated by this section. They like the multiple choice, they like the answers being there and people picking them, but often students are very apprehensive about the part 2 or the part B2 and part C or the free response section of this test because they have to deliver the answer out of their mind as opposed to pulling it out from a multiple choice question. So what I will say to everyone as we're going through this, if this is the first time you've gone through a part 2 with me, and if it's not, you know what I'm going to say is that the part 2, I'll be saying it part 2, but it's really part B2, part C, free response section, is really the same material as the multiple choice. Questions that are on the multiple choice of one test can wind up as being on the part 2 or the free response section of another test. The same concepts you see in multiple choice of other tests are going to appear themselves here. The only difference in this section of the test is they kind of cloak it and hide it a little bit by giving you more information and you have to pull it out. So as we go through this, please think, what concept is this question about? And oftentimes the question has nothing to do with the information they give you, or it's very much related but not exactly what they're showing you. So it's just a matter of understanding that the part 2 is about the same concepts as multiple choice, same concepts you've been learning. Just you have to be able to pull out that concept in their setup. So let's be crazy and start in order with this free response or B2 part C part of the test. And let's begin with 51. In number 51, draw a Lewis dot diagram for the chloride ion. Very important. You hear the word ion, you know it's charged. Now, of course, you see a charge given to you, but they could have just said chloride ion and not giving you this example. Remember, every time you hear the word atom, you think what? Neutral. Right. I say atom, you say neutral. And if it's neutral, that means the protons, which are positive, equal the electrons, which gives me an overall zero charge. Now, I say this because to figure out the number of electrons that act as dots, we have to know what the starting number of electrons are. So let's go to the periodic table. It's really the best way to understand what electrons are needed to do this Lewis dot diagram. Remember, the Lewis dot diagram is a diagram that shows the element symbol like chlorine, and it shows electrons that are valence, the outermost electrons. And the key here is knowing how many electrons to put around. So the starting place, if you don't know, is the periodic table. So let's go there. Okay, so I'm in the your reference tables, and I am just kind of zooming in on your periodic table. So on the periodic table of elements in your reference table, we're going to go to the upper right-hand corner. Chlorine's a halogen. It's group 17. And I'm looking specifically at the electron configuration 2-8-7. 2 electrons fill the first shell of electrons, 8 fill the second, and we haven't filled the final shell of chlorine, or at least we haven't filled that octet, is a better way to say that, because really more electrons fill the third energy level than 8, but the octet is a stable number. Like argon is stable because of that. So if you look, chlorine loves to become -1. That top number here is telling me the charge it loves to become, and a fancy word for charge is oxidation state. Now, all atoms written in the periodic table are or elements written in the periodic table are atoms. And I say atom, you think neutral. So the proton number, which is the atomic number that identifies the element, this is plus 17 in a nucleus, which means we need 17 electrons in the outside. But in this problem, we're looking for the valence electrons. Electron dot diagrams use the outermost electrons. So if I was to draw a Lewis dot diagram of chlorine, I would draw 7 electrons. But they said chlorine -1. And because it's still chlorine, it still has 17 protons. What makes it -1 is it has gained 1 electron. So this number is now going to be 8, just like argon. And that's why chloride ions are stable, or that's why chloride ions want to become -1. Chlorine wants to become -1 because gaining 1 electron gives it the electron configuration of argon, which is very stable. It doesn't become argon, but it becomes as stable with a filled octet. Notice all the halogens, group 17, all love to become -1 because they're one away from being stable. And stable is a low energy spot. Notice oxygen, sulfur, selenium, tellurium. They love to become -2 because they're 2 away. Notice nitrogen, phosphorus, arsenic like to become -3. Okay, so that's just some good reasoning there. So we need to draw a chlorine ion with um, with 8 electrons. So let's do that. So here we are in our answer booklet, and we're going to basically draw this number 51, and we start with the element symbol chlorine. Remember, chlorine we know is 2-8-7. These electrons are kernel electrons. These are electrons is in either. These are electrons that are in filled energy levels, and this is the valence electron, okay? And that, of course, are the ones that are available for bonding, the unstable ones. So we're going to draw, okay, 7 dots for the chlorine atom, but we have to remember they were asking for the what? The chlorine ion, which is -1. They gave us in the problem Cl -1, so this has to have 1 more electron, so I put it right there. Now, what we need is to show, in my opinion, brackets that this entire cluster here of the atom here and its outermost 8 electrons is now -1. Okay, however, they would accept chlorine with 8 dots and a -1 without brackets. Okay, but you needed to have that -1 there. Okay, and again, the brackets are really important if you were drawing a Lewis dot diagram of something ionic to show that this would not share electrons. Okay, but if you didn't have the brackets, it would work fine. But it's really important to do that if you, let's say you're having it show the bonding with sodium. Sodium lost its valence electron, and so you put the brackets here in +1 to do that, so that you're not implying that these are being shared. These are separate ions. Okay, so in any case, what we need here is just the chlorine with 8 electrons because it gained 1 to become as stable as argon, whether you put the brackets there or not. Okay, so number 52. So in number 52, we have some information given to us in the little blurb, I like to say, right here. And it applies to questions 52 and 53. Now, what happens a lot for many students is they read the blurb and say, oh my God, I don't know this. How, was I supposed to know this? No, this is just information that's related to the questions, and sometimes doesn't help you at all, okay, for the question. So if you look at this, if you read it at STP, chlorine is a gas and iodine is a solid. When hydrogen reacts with chlorine, the compound hydrogen chloride is formed. When hydrogen reacts with iodine, the compound hydrogen iodine is formed. Well, that's nice. And then 52 says balance the equation in your answer booklet for the reaction between hydrogen and chlorine using the smallest whole number coefficients. Now, I underline that because you remember some people can balance it without using the whole number coefficients. So they want you to balance the reaction. Whether or not you read this or not, you didn't need to know any of this to balance this reaction in number 52. So let's go to our answer booklet and just balance the reaction that they gave us. So let's go ahead and do this. So we have 2 hydrogens, 1 hydrogen. Remember, when you're balancing a reaction, you're basically following the law of conservation of mass and charge, okay? But since none of these have charges on both sides, it's going to be 0. But in any case, we have 2 hydrogens. We only have 1 hydrogen here. The only way we change this is by throwing a coefficient of 2 here. Now this makes 2 chlorines, right? We have 2 chlorines. And there you go, you're done. Now whether you want to put, okay, ones in front or not, it doesn't matter. But this is all we need to do here, okay? All we need to do here is put 1, 1, and 2, okay? Or again, if you wanted to look at it that way, or you could have just left it alone and say, well, why does that work? Well, it works that way because if I have a hydrogen, I have one of them. Kind of like if I have an apple, I have one apple. You don't have to tell someone I have an apple. One apple if I have the apple. So this is, one is implied, so whether you put there or not. What I will say, though, is that sometimes in some questions I'll ask you for the sum of all the coefficients, and if you put the ones in, it reminds you that the sum of all the coefficients, if they're balanced with their lowest whole numbers, okay, would be 4, okay? But they didn't ask that. Now careful, the question did ask for the lowest whole number, because some people could balance by putting a 4 in this place and then putting a 2 and 2. That would balance as well. So they always want the lowest whole number, and they were reminding you that. So that's why we're going to stick with the 1, 1, and 2, or nothing in front, which implies 1 and 2. Pretty straightforward, number 53. Okay, so number 53, explain in terms of intermolecular forces why iodine's a solid at STP, but chlorine is a gas. Now, this question is based upon this blurb, but as I've been saying, a lot of times this blurb is more information than you need, and a lot of students get intimidated by what's in here. But we don't need anything in this statement to answer this question. They're telling you iodine's a solid, but chlorine's a gas. Now, what is a solid? Okay, well, a solid is a three-dimensional geometric repeating structure of how, in this case, iodine molecules would exist. Okay, I'm just drawing a very simple cubic structure, but I'm trying to remind you, okay, and of course this would be I2, so this is how I2 possibly, and I don't know the exact structure, but the bottom line is, okay, this is an I2 particle, and it would arrange itself in some kind of crystalline pattern. That's what solids do, and it goes in all directions, comes out, goes in, and you need to know that a regular three-dimensional crystalline structure, geometric pattern, is what solids are. So crystalline structure, or crystal, I'll write crystalline because you'll hear that word a lot, is screaming to you a solid. Okay, now if these particles, I2 particles, okay, and we can call them diatomic molecules, all right, and we can say that the crystalline structure, okay, these guys are held much, much stronger. Solids, the attractive forces in the solids are much stronger than they are in a liquid. Now, I say liquid because liquids are not bound by this three-dimensional arrangement. Now, if you remember, solids can only vibrate in their fixed positions. Now, if you give them more heat, they vibrate more. Remember, temperature is a measure of the average kinetic energy. So these things would vibrate more. If you give them even more heat, they'll pull away out of their crystalline structure where they can basically translate and move more freely. So, and of course, if you're talking about a gas, okay, a gas is going to basically fly around the room hundreds of miles an hour. Liquids will kind of stay in their, will definitely stay in their container, take the shape of their container. The bottom line here is that solids are in this very stable, low energy arrangement and can only wiggle in their fixed positions because the intermolecular forces are stronger that keep them from moving that much. And of course, liquids and gases have much more freer range of motion because they have higher kinetic energy. And you should really know this, okay? Because if you think about a heating and cooling curve, all right, and you talk about kinetic energy, which is what a thermometer measures, you've got this very basic what? A heating curve, and this is the solid, liquid, and the gas, which has tremendous energy. So you can see that the gases are higher up in the kinetic energy. So gases and liquids have more energy than solids, and therefore the attractive forces must be weaker. Remember, an ideal gas is considered to have no attractive forces. All right, so let's get our answer down to number 53. So I put iodine has stronger intermolecular forces than chlorine. That's a really good way to answer the question, because remember, these are not very difficult questions, but they definitely wanted you to answer these in terms of the intermolecular forces. So not answering them in the way they want to, you can get this wrong. And of course, iodine has stronger intermolecular forces because it's a solid. You don't have to say that. You could say the forces between chlorine molecules are weaker. You could say the dispersion forces, or we would say LDFs, London dispersion forces, are stronger than iodine. Why? Because iodine and chlorine are both nonpolar particles. The molecules of I2 attract each other more. All of that works. There's many ways to say this, but it had to be in terms of the attractive forces between the iodine and the attractive forces between the chlorine in their structures. Okay, gases obviously have weaker intermolecular forces of attraction. That's why they are gases. That's why they're able to, fly around the room hundreds of miles an hour. Number 54. Number 54, identify one chemical property of sodium from this list. All they want is one. Please look at the question carefully. So we have some chemical and physical properties. And what do we know about chemical properties? Well, chemical properties, okay, are always making a new substance. A new substance. Now, what is a substance? Now, I'm using an answer with a vocabulary you may not know. A substance is a compound, which we should know to be two or more different elements combined, like HCl is a compound. It has a unique chemical formula, a fixed ratio of elements, and also an element is a substance, and substances are homogeneous. Compounds are made up of the same molecules, and elements are made up of the same type of atoms because they have the same number of what? Protons. So a chemical change is when a new substance is made on the product side, where a physical change is a property where you don't have to change the chemical. There's no change. Now, what creates the change is that bonds are broken and bonds are reformed. This change is about chemical bonds changing, right? Okay, whereas in a physical change, you're not, or in a physical property, you're not involved with breaking bonds. For instance, density. When you measure the density of something, it's mass over volume ratio, you don't have to test it chemically. You don't have to break bonds and see new substances. You just take that substance, you figure out its volume, maybe by measuring, and you mass it on a scale, and you can get the density without breaking bonds or changing the substance. So which of the following represents change of the substance? Well, being a soft silver colored metal are properties we can measure that do not change the substance. And melting, although it sounds like something is changing, melting is a phase change. And a phase change, when you go from a solid to a liquid to a gas, okay, tremendous energy there, these guys are not changing their chemical formula. Ice, liquid water, and water vapor all have the same chemical formula. You're just changing the distance between the molecules. So where do I have change? Well, we see it oxidizes. Hey, oxidation, that's Leo, right? Losing electrons. Hey, I'm becoming something else. I was sodium, and when I lose electrons, I become sodium plus. That's not the same form. So that is a chemical change. We're going to make new ionic bonds. Electrons are being passed around, and bonds are about electrons being shared and or being transferred. So this is speaking to a change in those chemical bonds. So that could be an answer. Forms compounds with non-metallic elements in nature. Hey, it's forming new compounds. That's a chemical change. And forms sodium chloride, which is a new compound if it starts with sodium, if it reacts with chlorine gas. So these three right here, okay, these three are, any one of these three would work out perfectly. So pick one of those three. So in the answer booklet for number 54, I say sodium reacts with chlorine to form NaCl. This speaks to, again, I'm making a new substance. Bonds are being formed, okay? Or I'm making a new arrangement, making a new substance. Again, I could have picked any of the three choices we just spoke to. I just wrote this one down. They just wanted one. So number 55, let's go. Number 55, convert the melting point, which is a temperature, to degrees in Celsius. So they gave us it melts at temperatures of 371 Kelvin, and they want to convert that to Celsius. Okay, well, we have a converting formula, or a formula that helps us convert. Let's go to table T, which will show us that. So looking at table T here, let's scroll down, and we'll look for temperature, and there is our formula. Kelvin is equal to Celsius degrees plus 273. Notice Kelvin doesn't have a degree symbol. That's kind of cool because Kelvin actually uses the Celsius scale. Okay, it uses the same size degree as a centigrade scale or Celsius scale. It just starts 273 degrees sooner. So you should know that a Celsius and a Kelvin change in temperature are the same because a Kelvin and a Celsius are the same size. It's just that Kelvin starts 273 degrees sooner. So let's use this formula to solve for that problem. Now notice, my friends here, they are not saying show the work, right? They just said convert. So they're just looking for the answer. They would tell you if they want to see the work here, right? So what we're going to do here is we'll just do it here. It wouldn't matter wherever you put the work. Okay, they're not looking at it, just looking for the answer. So from table T, we know that Kelvin is equal to Celsius degree plus 273. So we're going to put 371 here for the Kelvin, and we're going to solve just like table T showed us. 371 Kelvin, and solve for C algebraically. And so when you solve for C, you're going to go minus 273. That, of course, goes to 0, minus 273. And when you do the math, C degrees, or Celsius degrees, equals 98. All right, so let's put that in. And of course, we are writing it into our booklet. And number 55, you can't put it where the test is. All answers go in the booklet. So number 55 is 98. Number 56. So number 56 through 58, we have this blurb here. And this blurb here has information that is related to these questions, but it may not be. And again, some students are intimidated by the information in these blurbs, and sometimes these questions are basically reading comprehension questions. So let's just jump to the question and see what it wants. Explain why H2O solid floats, why H2O liquid on H2O liquid when both are at 0 degrees Celsius. Why does ice float in water? And this is, of course, the reasoning why the Titanic was sunk, because the ice that was underneath, or the iceberg that was underneath the water, is what hit the boat and opened it up and caused that catastrophe. But the point is, all right, that the ice, or the iceberg, floats because of difference in density. And that's essentially the answer. The ice is less dense if it's floating, just like a helium balloon is floating up because it's the air in here is less dense than so the helium in the balloon is less dense than the air outside it. But if you did not know, you could go through the blurb to see if that could help you. Sometimes it can, and sometimes it's just pulling out an arbitrary fact or concept that's related to this. But let's go read, because reading is fun. At standard pressure, water has unusual properties that are due to both its molecular structure, its intermolecular forces. For example, although most liquids contract, get smaller, when they freeze, water gets bigger, making ice less dense than liquid water. And there is your answer, guys. So even if you didn't know that fact, okay, there it is in the reading. Now, I'm sure most people from at least earth science, okay, knew 56 without taking Regents chemistry. But if you didn't, they gave you the answer in the reading. So let's go to the answer booklet, because you're not going to write this in the test. You're going to put it in your booklet. So number 56 in the booklet, please. Let's go. And there it is, 56. When water freezes, it expands, making water H2O solid less dense than H2O liquid, right from the reading. Or you could just say, hey, the density of ice is less. Okay, the density of liquid water is greater. The distance between H2O molecules is greater in the solid phase. Many ways to say it, but it's about the differences in density. It's really important when you're answering this, though, that you specify who is more dense. This don't say it's density. If you just put density with more, so when you're answering this question, you need to make sure that you are specifying um, which is more dense. You just can't write density. So we would say that the ice is less dense than water. Water is more dense. You just can't write density down. Don't be that vague, okay? And try to write in complete sentences. It's really a good idea, although they will accept the fragments, the sentence fragments. So in any case, number 57. Number 57 is a question related to the blurb up here that was given, and it says, and I love to go to the question first if you can, if you're comfortable doing that. State the type of intermolecular force responsible for the unusual boiling point of H2O liquid at standard pressure. Now, what's so unusual about it, if you need to know, it says water has a much higher boiling point than most other molecular compounds having similar gram formula mass. That's true. Water is a pretty small compound with a very light molecular mass. Okay, oxygen is 16 grams per mole, hydrogen is 1. So when you do the formula mass or the molecular mass of water, you get 18 grams per mole. And it's pretty small. Okay, you know CO2 is a gas at room temperature. Obviously, we don't see CO2 puddles in our environment. The pressure is not high enough. So CO2 acts as a gas at room temperature, and so therefore, if you look at its molecular mass, well, carbon is 12, and this is 16 plus 16. The CO2 is 44 grams per mole, and I'm just saying this to show you that something so much heavier, okay, CO2 molecule per particle, is more than twice as heavy than water molecules, yet it's a gas. Well, why is that? It's because that water, okay, has intermolecular forces that are unusually strong, and they're due to something called H bonds. Okay, so water sticks together. What makes water very unique, its surface tension, all the properties we talk about it. One of the unique things is a type of attractive forces between the negative oxygen and the electron deficient H of this proton on the, or this hydrogen on the water molecule. We call it H bonding. Now it says bonding, but it's an attractive force. So if the attractive forces, or we say the intermolecular forces, are extremely high, then it's going to take a lot more heat for them to boil. Boiling is when, and it's a boiling point, is when the vapor pressure upward in water is equal to the atmospheric pressure pushing down. Bottom line, I think of boiling as maximum evaporation. So if these things are holding on tight, if water molecules, think of the water molecules as an individual particle, if they're holding on tight, it's going to take a lot more heat to get them to evaporate or maximally evaporate, which we call boiling, so a higher temperature. Now, we also know that from another table. So let's go to table H for a second. So looking at table H, and again, just something to connect you to the rest of the course with this question. We see waters over here, and we see these other liquids here, and we see vapor pressure. Vapor pressure is basically the force of liquid molecules escaping into the gas phase. So if this is the line, let's say, of water in a beaker, gases are escaping upwards. And as you increase the temperature, there are more gases escaping upwards. Therefore, the vapor pressure increases. This little dotted line is standard pressure. So when that vapor pressure equals a standard pressure, then we're going to get something called a normal boiling point. Normal means the temperature at which it boils when the atmospheric pressure is standard. Now, why is the line here for water so much flatter? Its slope is such lower number than these others because water resists evaporation. Its vapor pressure isn't as high at a particular temperature because the intermolecular forces of attraction are stronger. And the stronger intermolecular force of attraction is H bonding. So ethanoic acid and ethanol, actually these three all H bond with themselves, but water has stronger overall, okay, intermolecular forces of attraction than propanol or ethanol, and therefore it evaporates slower, and therefore it takes more heat to overcome those stronger intermolecular forces of attraction. Really important that you see that. So number 57, H bonding is the answer. Looking at the key from New York State, they also are accepting dipole-dipole. And I guess the reasoning behind that is dipole-dipoles is basically dipoles another word for having polar molecules. And it speaks to the fact that because water is polar, it's going to stick together stronger than other molecules that are non-polar. Okay, but really, really the best answer, and they're being very nice there, is H bonding. So let's go on to number 58. So number 58 is based upon this blurb above here, like as we've talked about, if you've been through question 56 and 57 with me. And as I said before, these blurbs sometimes give you the exact answer like they did for 56. Sometimes they're just related to the concept and they don't have the actual answer in there. So you can't always say that, hey, the answer to 58 is in this reading here. You can't always do it. Sometimes the reading, it parallels the concept. Okay, so determine the total amount of heat in joules required to completely vaporize a 50-gram sample of water at its boiling point. Boy, they're screaming to you that we are at a phase change because we're at its boiling point temperature and we're vaporizing liquid at its boiling point temperature. Now, what I would teach my students is that when we have this heating curve that you've learned, this being the solid, this being the phase change, this is the liquid, this is the liquid becoming a gas and all gas. So if you remember, this would be the solid, this would be the liquid, and this would be the gas, and this is kinetic energy. Now, they want to know the heat. That's the whole point of this question. They want to calculate the amount of heat in joules. All right. Now we have three different heat equations. Let's go look at them in table T. Here we are with good old table T. And we're going to scroll down and we're going to see the heat equations. And there's three of them. Q for heat in joules is MC change in T. They tell you what these things are. Specific heat, of course, is given to you in table B. And then we have Q times mass times heat of fusion. Heat of fusion is in the word for melting. And then energy, or Q equals mass times heat of vaporization. Okay, so you have three equations. Notice only one has a change in temperature. Let's go back to the question. So looking at our equation, we have Q equals MC change in T. That's a change in temperature. Now, this formula, MC change in T equal, would go right here. MC change in T. This is where you have a pure liquid. Okay, now we have two others. We have Q equals mass times heat of fusion. Now, fusion is in the word for melting, and that would go here. Now, you say, well, why was it go here, and how would I know that? Well, I'll tell you this. You can't use the formula for a change in temperature because at a phase change, there is no change in temperature. You can't measure the energy with this formula because there's no change in temperature. Remember, kinetic energy, the average kinetic energy is temperature, and it stays constant at a phase change. And you guessed it, the third one, Q equal mass times the heat of vaporization, would go right here, mass times heat of vaporization. Okay, and that's this phase change where a liquid's becoming a gas. Remember, the question stated, and they're going to tell you very, very clearly you're at a phase change. By him saying completely vaporize, he vaporizes when a liquid goes to a gas, okay, and then we're at its boiling point. So we're at the boiling point temperature, which means we're right at this point, we're at the phase change. So all this question is identifying which um, energy equation we needed. And of course, it's this one, which I like to write right in this area here. So Q is equal to mass times heat of vaporization. And they gave us the 50-gram sample, that's my mass, and I times it by the heat of vaporization. Well, where do we find that? Well, I mentioned before it's in table B. Let's go. So here's our reference table, scrolling down to B, and look what they give us. The heat of fusion, 334 joules per gram. Notice the units. Heat of vaporization, and if you have equation where there is a change in temperature, you'll use Q equals MC change in T, and you use this as your specific heat. So we need 2260 as that constant to measure the energy change at that phase change. Let's go and finish the question. So we put the heat of vaporization 2260 joules per gram. And we're going to solve for Q. Notice the grams cancel, and we're left with joules. and we put that in our calculator. And we get 11300 joules. And that is as simple as it gets. Let's go and put this answer into our booklet. So there it is, 113,000 joules. You could put a comma here. You could also be fancy and put the correct scientific notation in. Okay, so you could have done this as well. Notice they put the joules in for you, so no need. They weren't looking for significant figures when you do calculations. Yes, you should be aware of them, but and only very few questions actually ask for it. I've only seen it every few tests where I see one question. So in any case, put the answer down as your calculator, and there it is, 113,000 joules. Number 59. Okay, number 59 has a little bit of a blurb here that goes with the questions. And this could be helpful, this information, or it just could be information that parallels the question, meaning it may not be needed at all. Don't always think that the blurb can help you or always has information that'll answer your question. Sometimes they just kind of give you information that's related to a concept you should already know. Any case, 59, show a numerical setup. That's all they want. They do not need for you to answer for calculating the moles of tin oxide, okay, in a 3-gram sample. Whoa, they're giving you a 3-gram sample and they want moles. Well, my friends, in chemistry, all they want you to do is show you how you convert grams to moles. Now, we know that when we have a converting from moles to grams and grams to mole, we use the formula mass, the mass of the formula, using the atomic mass of the individual atoms to get the converting factor of moles to grams. However, party people, they have given us the gram formula mass, so we already have that. So we're going to convert 3 grams into moles, and let's do that in the answer booklet, but they just want the setup. Okay, so let's do that. So I teach my students, always write down what's given. We have 3.00 grams of tin oxide, and we know that we're going to get rid of grams, so we're going to use our units called dimensional analysis. Grams goes down here, and 1 mole equals how many grams? Well, they told us in the problem the gram formula mass of the tin oxide was 151. We got that from the blurb. Now if we didn't, okay, and there could be a scenario where we had to figure this out, and there could be a question that says, hey, what is the formula mass? We would look up the individual values of them, okay, and add them together. Whatever the atomic mass of tin is, plus 2 times the atomic mass of oxygen, and that would give us 151. Again, all they want is the setup, and that would suffice. Notice grams cancel to give you moles. Okay, so anything along the lines mathematically that would get you the right answer. Uh, they would accept 3 over 151 without any units. It's mathematically the same. They would set it, they would accept a proportion. Okay, so anything that would mathematically get you the right number, even though you may not have done it that way without using units. I would have taught this way, as most chemistry teachers would say to use your units, but if you, again, wrote it this way, or maybe you wrote a proportion like this, 151 is over 1 mole. I'm not a big fan of this, but this would give you the right answer nonetheless. In this case, 3 grams and equals X. Okay, so that would also, again, give you the right answer. So which one you use, up to you. I prefer this one, but all of these, rest of these would be perfectly fine and acceptable. Number 60. Okay, so number 60, determine the number of moles of tin liquid. That's what we're trying to find here. When 4 moles of H2, a different compound, they're giving us moles of H2, and they want another information about another chemical. That, my friends, is stoichiometry, and it's mole to mole. Now I'll show you both ways. The first way is how probably your teacher showed you, okay? And this is the way that I would teach it originally. I would take, okay, always write down what's given to me, 4.0 moles, okay, of my H2, and then they're looking for moles of something entirely different to get rid of the H2. I'm going to put H2 on the bottom, and I want tin, and I want to use the ratios. There's nothing in front of the tin, so that implies 1. H2 has a 2 in front, that implies 2. So the ratio of moles in my balanced equation, okay, is 2 to 1, meaning I'm going to produce half as much of the hydrogen. Hey, 4, half as much as 2, if you don't see that, okay. 4 times 1 divided by 2, and you're going to get 2.0 moles of tin, which is half that. Why? Because it's a 2 to 1 ratio. That's how it works. Okay, so that's my answer right there. However, again, we put that in our answer booklet, okay, 2.0 moles, and they weren't counting for significant figures, so you could have put 2 as well. But here's another way you could have done this, and I teach this to those students just to get the answer right, to figure it out. So in the question like this, where they're asking information, and you have to identify these questions, they're asking information about one chemical and they're giving you information about another, you have to go through the ratios. But another way to do it is say, okay, um, I have 4 moles of hydrogen, so I put the 4 right here. This is a mole-to-mole problem. You only have mole-to-mole Stoich problems, so this will always work. How many moles of tin liquid, SN? That's my unknown. Okay, well, how do I find that? Well, the coefficients become your denominators. 4 over 2. Remember, nothing in front implies 1. And what we have is 4 over 1, or 4 over 2, sorry, right there, is equal to x over 1. Solve for x. Cross multiply little hearts away, and you'll get 2. So let's put that in their answer booklet. Number 60 is 2.0 moles. Again, if you put 2 moles, totally acceptable. No significant figures were talked about or expected in this question, they would tell you. Number 61. Number 61 is based on this chart where we have a hydrochloric acid solution, A and B, concentrations and pHs. So the question states, state the color of methyl orange in a sample of solution A. Well, methyl orange is an acid-base indicator, okay? And you say, well, how do I know that? Well, hopefully, when we talk about color and we talk about the changes in identifying pHs, it rings a bell that we have a table, Table M, is a table that tells us how certain chemicals will change their color because their structure is changing in different pHs and their ability to absorb wavelengths of light. Bottom line is color changes with color acid-base indicators. Methyl orange is one of them. Okay, so you need to be able to recognize that this is a table M question, and they're saying to you that the pH is 2 for solution A. Through table M, what's the color of methyl orange at a pH of 2? That's what they're asking. Okay, identification of the problems or identification of the type of questions and where to go to is really important and imperative in this type of test. So let's go to table M. Good old table M, and we have methyl orange, and the pH in the question was 2. Now notice we have a red to yellow color change when the pH goes from 3.1 to 4.4. So anything greater than 4.4 is yellow. Anything 3.1 and smaller in acidic range, very acidic, a more acidic range, is red. And the color in between would be, I guess, an orange. So 3.1 and lower, okay, is going to be red. And so therefore, a pH of 2, methyl orange would be red. Just like bromothumba blue, at a pH of 2, anything 6 or lower would be yellow. Or litmus would be red if it was a pH of 2, because anything 4.5 and lower. So that's how you use table N. If it was above 4.4, anything 4.4 or greater is yellow, just like bromothumba blue. Anything greater than 7.6 is blue. So in this case, it's going to be red. So in 61, I couldn't help myself. I used red ink to say red. So number 62. In number 62, determine the hydrogen ion concentration in solution B. So the pH is 5. And what does the pH mean? The pH means negative log, which is a fancy way of saying take the positive value, P, of the H plus ion concentration. Look, in the example they gave you here, pH is 2. So if I have the actual concentration of the hydrogen ion, take the positive value of the exponent. That's how that works. We took the positive value of the hydrogen ion concentration, we made it a 2. How do we go back? Well, make it negative exponent base 10. So they're saying the same thing here. Given the pH of 5, how did a 5? Because this must have been the what? The positive value of this exponent. So 1.0 times 10 to the negative 5. Okay, and notice it's a much, much um, smaller number, and that's why there's less H pluses and the pH is rising. So the pH here is 5, which means the exponent was negative 5. Why? Because the negative log, or the little p, means take the positive value of the H plus, right? H hydrogen ion concentration. So 1 times 10 to the negative 5 will give you the pH of 5. Now they're starting you with 5, so going backwards, it must mean that the coefficient is negative 5 for the 10. All right, that's what they're doing there. But we learned this already. You should have learned this, that water loves to break apart. Okay, well, I wouldn't say it loves to. It does break apart a little bit into H pluses and hydroxide. It doesn't do it enough to conduct electricity, and that's why it's not an electrolyte. But if you were to multiply the H plus ion concentration times the hydroxide in water at a certain temperature, you get 1 times 10 to the negative 14, and there's your 14 scale. And if you have pure water, and because one water breaks apart evenly, both of these numbers are going to be the same, 10 to the negative 7. And when you multiply them, they give you 10 to the negative 14. And now if I add an acid, and I increase this number to, let's say, 1 times 10 to the negative 2, the pH would be the positive value of this exponent. And that's why the pH is equal to 2. All right. Now, of course, this number would go to what, when you multiply exponents, when you multiply numbers with exponents, you add the exponents. So what number plus 2 gives me 14 or negative 14? And you would say, oh, okay, that's negative 12 there. So when the pH is 2, this number is 1 times 10 to the negative 2, and the hydroxide, the basicity, is 1 times 10 to the negative 12. They get really, really small. And remember, because the pH scale is an exponent base 10, every change is a power of 10, meaning as the pH drops from, or the pH increases from 2 to 5, we would say that the basicity increased 1,000 times. Yes, 1,000 times. Why? Because 10 to the 3, this increased to 3. It's an exponent. 10 to the 3 is 1,000. And why do I say the basicity increased 1,000 times? Because as the pH rises, the hydrogen ion concentration gets smaller and the hydroxide increases. Any case, the answer is 1 times 10 to the negative 5, number 62. So there's your answer. You certainly could have just put this 10 to the negative 5 would have worked. You could have gave me the actual number that it represents. Remember, 10 to the negative 5 means you have 0.0004 and a 1. Remember, 1, 2, 3, 4, 5. So those are equivalent answers. It all mean the same thing. It's number 63. Okay, so here we got another blurb here. And again, there's a lot of information here that may or may not be needed. So don't think that your question needs to find something in this area. So we have also a data table that is going with this question that is definitely going to be worked on and utilized. So in 63, okay, in 63, we're going to state the evidence found in the data table that allows for the product of the pressure and volume, product means multiply, for the fourth trial to be predicted. Well, all right, if you need to read that we have a rigid cylinder, movable piston, okay, kind of like what we have in an internal combustion engine. It goes up and down, and the temperature is held in a constant way. The volumes of the three trials are measured and recorded. The key here is the question. State evidence found in the what? data table. Reread questions. Really, really good to refocus you, because if you go back into the blurb and it gives you all this information, very easy to get lost in the sauce and about what they're saying. Go back and read the question. State the evidence found in the data table. We're going to the data table that allows the product of the pressure to be, in the fourth trial, to be predicted. How can we predict this? How do we know what it will be? Well, because in the first three trials, the product of pressure and volume was constant. So we can expect, everything else being the same, that would also be constant. By the way, pressure and volume is inversely related. Remember, if we remember our graph, we get these asymptotic lines here. Don't be an asymptote. Here's pressure and here's volume. That's an inverse relationship. And if you think with me for a second, pressure times volume has to equal some number. Okay, let's make it equal to 20 for a second. Okay, let's do 1 and 20. Let's go 2 and 10. They all equal 20. Let's look what I just did here, party people. If you look carefully, okay, you'll see that if I double the pressure, 1 to 2, the volume halves. Hey, that's an inverse relationship. So pressure times volume equals a number that stays the same, is telling you that. But the bottom line here is that we can predict the fourth to be the same because the pressure times volume was the same in the first three trials. So I write pressure times volume for the first three trials is constant at 0.412. Okay, you could have said, as volume increased, the pressure decreased proportionally. There's no change in pressure times volume. Okay, PV is constant. Many ways to say the same thing, but they said look at the data table, so we can predict the fourth because the first three were equally kept or were at this value. So moving on to 64. In number 64, they want you to determine the pressure of the helium gas in trial 4. So they want you to find this value. Okay, so there are a couple different ways we could do this. Okay, first is to just kind of fill out what we expect. We expect pressure times volume to equal 0.412. I know it's not there, but we predicted that's going to be there for number 63. If we know the volume is going to be 1.373 and this number is 0.412, okay, let's go solve for P. Well, that's going to be 1.373 P, and we're going to divide both sides by 1.373. So P, just doing our algebra, is 0.412 divided by 1.373. Take out our handy dandy calculator, and we take 0.412 and divide by 1.373. So what we get is 0.300, and that would be good enough. Now, certainly we could do this other ways, and of course this is in atmospheres. Okay, if you're uncomfortable with that, could you do a gas law problem? And the answer is absolutely yes. Okay, so maybe many people did this. Now you could pick any other point. What we learn in table T, there's PV over T equals PV over T. Now we're solving for this scenario where the volume, of course, is going to be 1.373. So let's just put that volume there. So that's going to be 1.373. We're going to solve for this P. Something we should know from the top is that the temperature stayed constant at 273. So you could plug that in if you'd like and make sure that temperatures in a gas law problem are constant. I'm sorry, the temperatures in a gas law problem are converted to Kelvin. In this case, they're the same value, so they kind of cancel. They don't kind of cancel, they actually do cancel. So you could plug them in and solve for it, but I'm going to cancel them because they're the same on both sides. And then I'm going to pick a new point. So we're solving for a pressure at this set of conditions with this volume, I'm going to use another point. You could have used any one you want. So I'm going to make my pressure, okay, 0.6. So 0.60 here, and that's ATM. And then my volume for that point, and again, I can use any point. I just chose to use the one right next to it, 0.687, and the unit there is liter. And of course, you notice this was liter 2. So I do the math, remembering because the temperature stayed constant, this part cancels. So I'm left with this mathematical equation. And now I'm going to solve for P. P is going to be equal to 0.600 atmospheres times 687 liters, and then divide by 1.373 liters. And party people, you can see we can cancel out our liters. We're left with atmospheres. And then we use our handy dandy calculator, 0.600 times 687, and then divide by 1.373. And you get approximately the same number, as a little bit difference, but it's about 300 as well. And it's again 300, should be 0.300 atmospheres. And that should have been a decimal place there. That's what I forgot to put in there. That made my, so 0.600 times 0.687. That's the point that I initially forgot there. Divide by 1.373. Okay. And that gives you the 0.3 atmosphere. This is the same answer. And of course, the answer is in our answer booklet, where all the answers have to go, is 0.30 atmospheres. Certainly you could have put 0.3. There was no significant figures, so if you put 0.3, it's all good. All right, so number 65. Okay, number 65. This is a very, very good gas law question. I love it because it makes you think about how this all works. We have our gas law equations, and we've learned about different factors that affect properties of a gas, but when they make you really understand collision theory with this question. So let's talk about this. So compare the average distances between the helium atoms in trial 1 to the average distance between the heliums in trial 3. So we're comparing these distances in 1 and 3. And so what's happening here is, if you remember, we have some sort of a piston pushing down on a cylinder. Remember that volume, okay, is the space that the gas exists in. And of course, the pressure is the force over an area that these molecules, when they collide in this area, upward. Now, what's happening is that the volume is actually getting bigger. So from 1 to 3, we're getting bigger. So this kind of plunger pushing down is going up. And so the space is much bigger. Now, it's understanding that when we change our values of pressure, temperature, and volume, when we consider that, now, of course, in this discussion or this question, it's pressure and volume. Temperature has to be constant, and so does the number of molecules. Moles have to be constant as well. So, that being said, if I go back up and the gas particles now, and it has to be the same number, okay, now if the volume is bigger for the same number of gas particles and I'm at constant temperature, the pressure drops. Look at that. So the pressure was 1 when we had a certain volume. The volume got bigger, so this plunger was going up. We have more space, and giving the same number of molecules the same space, the distance is going to be greater at 3. It's the reason why the pressure dropped. The reason why when you push down on the plunger, the pressure increases is you're going to put the molecules in a closer space, and they're going to basically collide more often with the container walls if you make the space smaller. That's intuitive, right? So smaller the volume, higher the pressure. Well, the opposite is also true. If you increase the volume, that's what's happening here, the pressure drops because, well, there is more space between particles. There's going to be less collisions over the area. So we would say in trial 3 that because the volume is bigger, and now you're giving more space for the same number of particles at the same temperature, then the average distance must be greater in trial 3. And that's why the pressure drops. This makes sense if you have, 5 molecules. Let's just do 4. Make the container twice as big. I'm not a very good artist, but now, of course, gases always fill their container. Now you can see that there's more distance between them, and the pressure is actually cut in half, okay, when the space doubles. There's going to be less collisions because you think about it, now these 4 gas molecules have twice as much area to hit. Okay, so the collisions on the container wall decrease, and that's because there's more space between them. Okay, so let's go to the booklet. So I said the average distance between helium atoms is smaller in trial 1 than in trial 3. Or you could have said that in trial 3 the atoms are farther apart, the separation is greater in trial 3, atoms are closer in trial 1. So many different ways to say it. Okay, but a very good intuitive question that explains why the pressure increases when the volume gets smaller, or when the pressure decreases when the volume gets bigger, which is Boyle's law, an inverse relationship. Okay, number 66. So here we continue on with number 66, which is in the beginning of part C, which is again the same kind of blurbs given to you and questions that relate, and sometimes directly from this blurb. Oftentimes, again, as I keep saying it, this information just parallels these questions. So number 66, identify 2 types of chemical bonding in the source of dietary potassium in the cereal. So you don't know what dietary potassium is, so we go into the reading, and what do we find? Potassium phosphate is a source of dietary potassium. So what they're really saying is in K3PO4, all right, in K3PO4, potassium phosphate, what types of bonding exist? What 2 types? They're really being nice to remind you there's 2 types. So this is a part 2 question that's really attacking the concept that when you have polyatomic ions, clusters of nonmetals that have a charge listed for you in table E, I call that what the heck is that table, or table F, PO4 is given to you as -3. That's a cluster. And if you notice, there's 3 Ks. Well, K, or potassium, likes to become +1. We see that in the reference table, so clearly there's going to be 3 potassiums, each +1, that will have to hook up with 1 -3 to make this entire chemical formula, called an empirical formula, of this salt to become electrically neutral. And that's how we build these chemical formulas. We've done that. We put the ions together so that you figure out what the ratio of them to be neutral. But the question at hand is, what kind of bonds exist in this chemical compound? Well, the first thing, if you see a metal like potassium, okay, which is to the left side of the staircase, you know it's ionic. Okay, the question is, what are the others? Well, phosphorus and oxygen are nonmetals. So I'm going to write it up here for a second. So this is the phosphate, PO4. All right. Now, this -3 ion is going to attract 3 K pluses. I'm just going to write 1 ion. And the bond right here is ionic, don't you think, as Alanis Morissette would say. So ionic, because the bonds between ions are ionic. Ions, ionic, positive and negative attracting. So this is an ionic bond. Now, what other bonds do you have? And this is unique to polyatomic ions. Okay, well, in this cluster, okay, this bonding arrangement between phosphorus and oxygen, we should know them to be what? Nonmetals. The bonds between nonmetals are covalent. Yes. So therefore, if we have a salt that uses a polyatomic iron, this cluster, the bonds between the nonmetals are sharing. Yes, it's an ionic compound, metal nonmetals, But within this cluster of bonding, we are sharing electrons because nonmetals and nonmetals sharing. Well, how can it become negative 3? Somehow, some way that this sharing arrangement must have absorbed 3 electrons in its environment, probably from metals who are losing it, maybe from the potassium, who knows, to become stable. So this is a classic Regents question. I've seen this in multiple choice so many times. They just dressed it up, okay, for a part 2 question. So the two types of bonding are ionic between the ions and covalent between the nonmetals in the polyatomic ion. So anytime, now you have a polyatomic ion, like say here comes sodium carbonate. There's your metal, okay? So you're going to have your Na plus attracting the carbonate ion, which is CO3 negative 2. But inside this cluster, carbon and oxygen are nonmetals. That's a covalent bond. Okay, it's something you have to know. Going on to the booklet, let's do it. So we go with number 66, and how nice it was to give you the and in between the ionic and covalent. Wow, that's so nice they gave you that little and there. Number 67. Number 67, identify the noble gas, that's the last column, whose atoms have the same electron configuration as the potassium ion. Let's go to the periodic table. So here's your periodic table of elements in your reference table. And I can see that this staircase delineates my what? My nonmetals from my metals. But look at potassium for a second. Let's get up close and personal here with potassium. So potassium is an atom. All elements written in this periodic table are atoms. They're elements. Groups of the same elements have the same number of what? Atomic number of protons. This charge tells you the charge they like to become. They call it an oxidation state. Now, why does potassium like to become +1? Well, look, its configuration is 2 electrons in the first energy shell, 8 in the second, 8 in the third, and 1 in the outermost. So all atoms want to achieve stability, the lowest energy possible. And the way they achieve stability, the lowest energy possible, is achieve a noble gas configuration. Now, potassium could achieve a noble configuration if I go across and become like what? Krypton, by having what? 18 in its third and 8 in its what? Outermost. Okay, that's going to be hard for it to do. It's easier for it to lose this last one. And of course, metals hold on to electrons loosely. So if it loses this last one, then it's 2-8-8. And who is that? 2-8-8 is argon, or as we say in an industry, argon. Okay, so in any case, 2-8-8 is what the configuration of potassium becomes when it becomes +1. Notice chlorine gains 1 to become 2-8-8, okay, when it gets stable. Notice sulfur becomes -2 by gaining 2 to have 2-8-8. In this course, we're dealing with the octet rule. So potassium, to have an octet, it'd be easier for it to lose what? 1 than to gain 7 more. And because the metals lose electrons, that's what it does. It becomes 2-8-8. So the answer is it becomes the configuration of argon. So argon is the answer. You certainly could write the symbol, element. You could say element 18, all good stuff. Number 68. Okay, number 68. Compare the radius of a potassium ion, that's a charged atom, to the radius of a potassium atom. I say atom, you say neutral. Atom, neutral, you're supposed to say. Okay, so compare the radius of a potassium atom. Okay, well, we've got potassium. I went there, I'm sorry. Compare the radius of a potassium ion to the radius of potassium atom. Okay, so let's start with the potassium atom. Okay, let's just make a circle. Now, potassium, like all metals, are pretty big. And then when they become an ion, and I'm moving it this way because I always show that the atom becomes an ion. I think this kind of question is kind of phrased a little bit differently, probably in a way to try to get you to get this wrong in a sense, because I would love to say, compare the radius of the potassium atom to the ion, because atoms become ions. So this is the atom over here. All right. And when it becomes an ion. Now, what ion does it become? Well, from the previous questions we've just seen and looking at the periodic table, potassium has one valence electron. It likes to lose it to become stable like argon. That's what number 67 was about. So this becomes positive. Now, notice it's still potassium. It's an atom of potassium, and it's a what? It's a ion of potassium, which means to be potassium, you have to have atomic number 19. I'm sorry, yeah, atomic number 19. Now, atomic number 19 is unique for potassium. That means there's 19 protons. So the proton number does not increase. If it did, okay, this would now become calcium. Calcium's atomic number 20. But since the atomic number is staying constant, which means the number of protons are staying constant, what gives the atom its nuclear charge in a nucleus, its positive, is a proton number. So the only way for this to become positive is that electrons were lost, okay? And that makes sense because losing electrons is oxidation. Leo the lion says grr. So losing electrons is oxidations. Metals like to oxidize by losing electrons. So the question is, when you lose electron, what happens to the radius, okay, when you become an ion? And again, I think this question is really phrased in a way that you can get this wrong. But in any case, the atom becomes an ion by losing electrons. Now, if you're losing electrons, but the proton number is staying constant, that's what's happening here, then the protons outnumber the electrons. Now, when we say atom, you say neutral. Potassium has 19 protons, and therefore it has to have 19 electrons, which each one is -1, because when you add these together, okay, you're going to get 0. So the protons give you the 19, that's the atomic number, but the atomic number also equals the number of negatively charged electron particles, and that gives the atom its neutrality. So this is 19 electrons. They could have asked for how many electrons. Now it's 18 electrons, but the point is you're losing electrons, and now you have 19. In this case over here, you've got 19 protons, but now you've got 18 electrons, and now there's a little more positive charge than negative charge, and that's going to pull these electrons in. So that must mean that the ion has to be smaller. Okay, when you lose electrons, the ion compared to the atom gets smaller. So when you compare the radius of the ion, the radius of potassium ion is smaller than the radius of the potassium atom. Now, they could ask in another question, and I'm just going over this topic so you understand it fully. The one way to remember that losing electrons, the ion gets smaller compared to its atom. And they could phrase it this way: the ionic radius is smaller than the atomic radius. And the reasoning is losing electrons always makes the ion smaller than its atom. And think of it losing weight. When you lose weight, you get smaller. And the opposite, of course, like nonmetals like chlorine, when they gain an electron, like we call that reduction, gaining electrons, they become negatively charged ions. They get bigger as an ionic radius compared to the atom because they're gaining electrons, and there's one more electron compared to protons. Or just think, gaining electrons, like gaining weight, you get bigger. Okay, so let's go to the answer booklet. So for number 68, the radius of the potassium ion is smaller than the radius of the potassium atom. Really good to phrase your question in a sentence that really brings up both. However, you could have said the radius of the atom is greater, or the K plus ions are smaller, or something along the line like K plus is smaller than the K, and all of that would have worked. Okay, but it really is good to mention both things. Remember, they're asking you a certain question. You must answer it how they're asking you, and they wanted you to compare both the ion of potassium and the atom. Number 69. So number 69, the fourth question based on this little blurb here. And most of these questions had very little to do with the blurb, so don't try looking back in them. Okay, number 69 is probably the question that really required more information than the others from that little blurb. So let's go into it. The mass of potassium in a 1 cup serving is determined to be 172 milligrams. Show a numerical setup for calculating the percent error for the mass of potassium in the serving. So if we're doing a percent error, we're taking a measured value that we get from an experiment. So it looks like to me that the mass of potassium in a 1 cup serving of this cereal is determined to be this. So this is my measured value. So what's my known value? Now I'm going to have to go back into my blurb, and it looks to me that the known value is 170 milligrams. Let's read it. The accepted value, here we go, the theoretical for a 1 cup serving in this cereal is 170 milligrams of potassium. So it looks to me the accepted value, or the known from some standard, is 170. So we're doing a percent error. We need to know what is the experimented or measured value and which is the known. So let's kind of wipe away some area here to do the math. They're looking for a numerical setup. So I guess we do not have to solve for it. In fact, you do not. So just a numerical setup is what they want here. All right, there's nothing wrong with calculating it, but no one's going to look at it. So let's go to where we can find what the percent error formula looks like, because maybe you didn't know that you needed both the known value and the measured value. Okay, if there is a percent error, there's a formula to calculate the percent error. Let's go to table T. So here's table T in all its glory, and here we have our percent error formula, which is percent error is the measured value, that's from the experiment, minus the accepted, over the accepted times 100. So given that formula, let's just plug in our values. That's all they're asking to do for this question. They just want the setup, the numerical setup. So let's do that in our answer booklet. Okay, so from table T, it's the measured value minus the accepted over the accepted value. So from the reading, okay, which one was the accepted and which one was measured? Well, let's go back because my short-term memory is gone at this height. So let's go find that measured and accepted value. So the accepted value is 170. They even said it exactly the way it is. Sometimes we say theoretical, but there it is, one's accepted. And this one was what was measured. It was determined to be 172. So 172 is measured and 170 milligrams was the accepted. So 172 milligrams minus 170 milligrams divided by 170 milligrams. It's that simple. Okay, they just want the setup. Now you didn't have to write all of this. I just put that there to show you, if you had table T in front of you, how you do that. Notice it's measuring accuracy, how close we are to the known standard. The hardest part about the equation was knowing that I wanted percent error if in fact table T had a nice formula for you, and more importantly, which one was measured. Since in the reading they said this one was accepted, okay, I think it made this a pretty simple question. Okay, so coming on to number 70. Number 70. So we've got another blurb here, and it's a very small one. I'm talking about photosynthesis, but here comes the question. Write the empirical formula of glucose. Now you say, oh my gosh, I don't know glucose, so you may have to go back into the blurb, and we see that I'm blurbing out blurb, that glucose is C6H12O6. There it is. So they want the empirical formula. What is the empirical formula? That is the lowest ratio. So C6H12O6, what does that reduce to? Isn't that really a 1 to 2 to 1 ratio? So the empirical formula would be CH2O. And we use empirical formulas when we do analytical chemistry, where we're using masses to find percent by masses. So in a certain type of analytical type of laboratory procedure, we would be able to come up with the mass, okay, or the percent by mass of carbon. And knowing the mass or the percent by mass, we can get the lowest ratio only. But so this is called the empirical. Now it doesn't look right when these things are molecules. Now when they're a molecule, this is the formula they actually have to be, so that all the electrons in the covalent bonding, remember molecules make covalent bonds, they're called molecular compounds. And this is the exact arrangement of atoms you need to make all of this work. And we call this a molecular formula. A molecular formula is how the formula actually exists in nature, and the empirical is the lowest ratio. Sometimes you have both. Let's do another one that doesn't though. Let's look at hydrogen peroxide, H2O2. That's exactly how it bonds. You need two H's and two O's to satisfy all the octets or the two electrons for the hydrogen. And when you find it in the lab, you come up with HO. Ho, that's the lowest ratio. Now there are chemical compounds like water that are already in their lowest what formula. So this is the molecular formula of water. It's a molecule, and it already is in its lowest ratio just by a hook and crook. This is already in its lowest ratio. So water is both its molecular, how it exists in nature, and its lowest ratio, 2 to 1. So there are some compounds that do that. But I do want to make sense that the empirical formula feels very strange for molecular compounds, because this would never bond this way. Carbon must have 4 bonds. What it's not strange for are salts. Salts, or ionic compounds, are always in the lowest ratio. Case in point, if I said to you, what's the chemical formula for calcium oxide? You say, oh, oxide just means you just have oxygen and calcium. So I look up the charge of calcium. It's +2. It's an alkaline earth. They're all +2 because they have 2 valence electrons. Oxygen, I look up the charge it likes to become. Upper right hand corner is -2. Some people learned that, hey, to make this, I crisscross. Okay, but you're looking to make a neutral compound, so some people would write Ca2 and O2, and that would be wrong. Salts are always the lowest ratio of ions in a crystal. So there's 1 calcium per 1 oxygen. It should be CaO. So salts are always empirical, and molecular, how they have to exist in nature and molecular. But if we call molecular formulas. In any case, the empirical lowest ratio is CH2O for glucose. And there we have it for number 17, the lowest ratio of glucose, CH2O, a 1 to 2 to 1 ratio, number 71. All right, so we're going to do number 71. State the evidence that indicates photosynthesis, which is this reaction they talk about in the blurb, is an endothermic reaction. And my friends, in chemistry, I see energy. Don't fall for the fact, hey, it's light energy. It doesn't matter. Energy is in the reactant side. This is the reactant side. Notice where the arrow is. That means energy has to go in. Look at the arrow. It's before the arrow. That means that these two chemicals overall need a tremendous amount of energy to become the products. Now, this is not activation energy. This is the energy needed. If you were to draw a potential energy diagram, okay, I'm sorry, yeah, potential energy diagram, let's call it that. And it's endothermic. That means this is the total potential energy, which is really the energy of bonds of my reactants. This is CO2, and this is 6 H2Os collectively. So all of the bonds, and there's 6 of these too. So all the bonds in CO2 and H2O, okay, their potential is this right here. Now, of course, we have an energy barrier. That's the activation energy. And then we come and we make our products, which are C6H12O6 plus 6 oxygens. And if you look here, party people, you'll see that we started low and high. The difference of where we start and finish is our delta H. And you should know that delta H is positive here because we're going up in energy. And so this is endothermic. How do we start low and finish high? Energy must be absorbed. Now, I like consumed because it's using that energy. Now, in the case of photosynthesis, light energy with CO2 and H2O is being used to break all these bonds and reassemble them into something that has a lot more energy. Glucose we eat for energy, okay? And we're starting with very low energy stable compounds. We need the energy to get up to put the energy into the glucose. Any case, so you think of endothermic reaction, you think of energy going into a reaction, and you're going to see the energy on the reactant side. If the energy was written on the other side, let's pretend that the energy was here. It's not. If it's following the arrow, it's leaving the reaction, it's exiting, and that's exothermic. So this is going before the arrow, it's going into something, it's being absorbed, endo. If it was if the energy was written at the end, it'd be leaving after the arrow, exothermic. So let's go on to the booklet. So in number 71, photosynthesis is an endothermic reaction because light energy is absorbed or consumed. Now you certainly could say the energy term is on the left side of the equation. Delta H is positive. The reaction requires energy or light. Many ways to say this, but the key to the problem was seeing that energy was in front of the arrow. So that's really key. All right, number 72. Number 72. Explain why electron configuration of 2-7-1-1 represents a sodium atom in an excited state. So 72, 73, 74 are based on this blurb. And as I just showed you, I think it's really important to read the question first because, again, so many people look at this information and sometimes get intimidated and think, I don't know what's going on here. And then you can't answer the questions or you convince yourself you can't. Go to the question. In fact, I read the question 72. Really, although there's some information here that parallels the information or it's very similar to what you're talking about, I don't need this. I don't need any of this to answer why this is an excited state. Don't think that every question in this free response section, okay, the answer has to be in this blurb. It's not. So they're just giving you a question that's based on fireworks and colors and why is it excited? So why is it excited? Well, let's go find the sodium atom. And when I say atom, you think neutral. So I'll say atom, you say neutral. Atom, you're supposed to say neutral. Very good. So atom, neutral. Say it's a dance party. So let's go to the periodic table to see what the sodium atom's configuration should be if it's in the ground state. Grounded, low energy. Let's just go there. So we have our sodium, and if you notice, it's atomic number 11, and because they're all written as atoms in the periodic table, this tells you the charge you like to become. This is not what we're dealing with. People get confused and say, oh, it's sodium plus 1. No, it's just sodium. It's magnesium. These are atoms. Neutral, right? So if it's neutral, the positive protons, remember that proton number identifies the element, has to equal the negative electrons. So this is 11 protons and 11 electrons. So when they say excited state, they're not talking about the charge it becomes. They're talking about electrons that are jumping from their lowest energy positions to become excited. So the configuration here, and if you didn't know this, this means 2 electrons are in the first shell, 8 exist in the second, and 1 exists in the third. Notice it has 1 valence electron, 1 electron outside filled shells. Now normally the filled shells have 8. The first one has 2. All right, that's why helium is stable, because it's atomic number 2, 2 electrons also. But in this case, this is written as a ground state configuration. These are electrons filling lower energy orbitals first, meaning always think of the nucleus in front of the configuration. So there's 2 electrons that fill the first shell, 8 in third, and 1 in the third. Now notice when you add these together, 8 plus 2, 10, and add 1 more, you get 11 because it's an atom, neutral. So these electrons will always equal the atomic number. And I say this because even though this question is in part 2 right now, you may see a question in the multiple choice says, which of the following is an excited state configuration of sodium? And I want you to remember that an excited state just means that the electrons are going out of order because they're leaping away from their ground state, but the number of electrons will always equal the atomic number because it's still an atom. It has nothing to do with being an ion. They wanted the excited state. So let's start with 2-8-1. Let's go back to the booklet, back to the test and talk about this. So we have sodium, and from the periodic table, we know the configuration is 2-8-1. Now, as written in the periodic table, they give you something called the ground state. And if you've ever been grounded by your parents, that means you're in your lowest energy position. You can't do anything. You got to stay in the house, maybe stay in your room, who knows? The point is, that's the lowest energy position, and that's where the electrons fill their lowest possible energy states. Now let's talk about this. We have a positive nucleus, okay, because of the protons. There's neutrons there, but they don't have a charge. And then we're going to have, and again, I'm going to draw these shells or orbitals of electrons, okay, but we're going to draw them as kind of orbits, okay? Even though they're not, they exist in these three-dimensional wave functions called orbitals. But we're just going to make this a proximity, diagram, and we can do that. It works very well. Okay, it's really the Bohr model here. But we have 2 electrons here, and then we have 8 electrons in the outermost, or it's the second shell. So 1, 2, 3, 4, 5, 6, 7, 8. And then we have 1 in the outermost shell. So that's why we get 2-8-1. That's what it means. Now, I need you to understand this, though. The electrons that exist in energy shells or orbitals that are closer to the nucleus are the ones that are, of course, in front. So this is like the nucleus is right here. Always think about this. So these electrons are closer to the nucleus, and that's true no matter if we're using the orbital, the Bohr model here to do this type of explanation. It works very well whether we're using wave mechanics or the Bohr model. But the bottom line is that these electrons are closer to the nucleus, so they feel this positive tug or this force. Therefore, these guys are less free, and therefore these electrons, okay, this shell has the lowest energy. And when we say low energy, we say stable, okay? And that's why electrons will fill the low energy first. So we got 3 electrons, there'll be 2 in this energy, then here. So in this case, we have 11, 2 will fill here, then the 8, then the 1. Now the outermost shell, where the valence electrons, these electrons that don't feel the nucleus as well, have higher energy. Now again, why? Well, I kind of gave that away. These electrons are, proximately speaking, are farther away. They feel the nucleus less. So they're higher energy. These guys are able to move a little bit more, and they have more freedom. In fact, these are the electrons that become the ion. So when sodium becomes Na+, this is the electron that's lost, not these, because this one feels the nucleus less because it has higher energy. So when we say an electron configuration is excited, what we're saying, party people, is that an electron that's in a low energy position, okay, let's just say it's this one, jumps farther. Let's not say that one, because let's just stay with this diagram here. Look at 2-7-11. And you think about that, that's an excited configuration. Okay, so let's talk about what happened here. It's supposed to be 2-8-1. So if you think 2-8-1, that 8 is now a 7, right? That's now a 2-7-1-1. So what just happened is an electron from the second shell jumped to the fourth. Well, Mr. Grotsky, though, I don't see a fourth. Well, it's there, just there's no electrons there. Okay, so let me just draw it there. So an electron jumped there, and now it exists in this state. Let's get rid of this electron here if I can. Okay, sort of. And let's make sure that I rewrite this 8 and make sure we can see this electron. So this electron that was here, okay, now is over here. And there's our 2 dash, well, not anymore 8, it's 7-11. And so an electron that was closer to the nucleus somehow jumped farther away. How'd that happen? Of course, you need energy, right? So energy was done through that. So this is important, and I'm explaining a lot here so you understand what happens. You have to understand electrons closer to the nucleus have lower energy, electrons farther away. So for an electron to become excited, have a lot more energy, it has to overcome the positive pulling attractive force of the nucleus. Negatives and positives attract. So to overcome this positive force, this attraction, energy is needed. So explain why the electron configuration represents sodium atom in the excited state. Well, it represents sodium atom in the excited state because an electron that was in a ground state, its lowest energy position, just absorbed some energy to move farther away. Okay, so that's what this is about. All right, so it's in a higher energy state because this electron now feels the what? Nucleus less. There's many things we can say, but very important that we didn't lose an electron. If you look at this configuration, 7 plus 2 is 9, plus 1 is still 11 electrons. We're not becoming an ion. We're an atom, neutral. Okay, so this diagram, everything I drew here, is important for you to understand what is happening here. Okay, so explaining why the electron configuration becomes 2-711, okay, all we're thinking about is an electron that's in a lower energy shell moved to a higher energy cell, or that it gained energy. Of course, it has to do so to become excited. All right, so there's many ways to say that, but let's go to the booklet. So in our booklet, we can say an electron in a lower energy shell, more stable shell, now you don't have to write that, but has moved to a higher energy shell, which is more unstable, okay? And you need to understand this in terms of how electrons transition. Certainly I could say the configuration represents a higher energy state than the sodium's ground state. Not all 11 electrons are in their lowest possible energy levels, okay? Um, so many ways to say this, okay, but I think this is the best way. But you have to understand the nucleus and electrons that are closer, okay, are more stable and low energy, and for them to jump away, they have to grab energy. Okay, energy goes in. All right, so in any case, an excited state atom means that we have the same number of them. And I say that because of the multiple choice questions that could come up with in this area. All right, moving on to 73. Okay, so number 73, and I know I have whited it out to do the question, but I want this diagram here. So 73 states, and it's right here underneath, explain in terms of electrons how a strontium salt emits colored light. So again, number 73 says, explain how the strontium salt emits colored light. All right, so if you're not really sure what they're talking about, let's go back to the blurb. Fireworks contain metallic salts, such as sodium, strontium, and barium, can generate bright colors. So they actually call these stars. They put these actually in fireworks and they burn them. And because you give these atoms or these compounds energy, electrons are able to jump away. Okay, a technician investigates what colors are produced by the metallic salts performing flame tests. You may have done this in a lab. During a flame test, the metallic salt is heated in the flame in a gas burner. Each metallic salt emits a characteristic colored light. So the question number 73 states, explain in terms of electrons. You have to be careful how you answer the question. So in 73, they said, explain in terms of the electrons how strontium emits colored light. Well, in number 72, I just explained why electrons jump farther away. So now in 73, they want you to explain why they give off the light, and that's leaping back. So let's step back. If I didn't review 72 with you, understand that in 72, we dealt with electrons jumping away to a higher energy orbits, or orbitals I should really say, because the orbitals that are farther away from the nucleus are in the third and fourth shell. So over here we're farther away physically from the nucleus, and therefore we feel the nucleus less, and therefore these shells, or I should say orbitals, are what? Higher energy. The farther that we go away from the first number, it's the first shell, which is closest to the nucleus, the more free the electron is because it feels the nucleus left. Well, why does it feel the nucleus left? Or why does it even feel the nucleus? Is because positives and negatives attract. And if this negative is farther away, it feels it less. Okay, so these are higher energy orbitals. I tell my students all the time, if you don't quite get this, think about going to school with your mom or dad, right? And so they're following you around and you feel them right on you all day long. You'd have less freedom. Now, if they're not with you in school, you may not dance on the tables or go crazy. You might be good students and good people, all that being said, but without your dad or mom there, you have more freedom probably. You feel more relaxed. So same idea, okay? Now, of course, there's some people that act really different when they're away from their moms and they have higher energy, and that's basically the analogy I'm making. So we need energy for electrons to get excited. You need to give this electron who is feeling a nucleus more energy to get to a position that requires more energy, right? You need to be freer. If you don't have the energy, you get pulled back to your ground state. Closer to the nucleus, feel the positives more. Farther away, you feel them less. So excited state. So in order to have a colored light, the first step is that electrons have to be excited, okay? And so any case, when they're excited, for instance, in the example in 72, we took an electron, I know I have an arrow here now, but we took an electron from the 8 filled octet of the second energy level, and it jumped to the fourth. It was 2-8-1, now it's 2-7-1. So this electron jumped here. Now it's unstable, has high energy because it needed the energy. It has it. It overcome, but it's not going to stay that way. Think about, going into the city and there's an unstable person, so much energy, you don't know what they're going to do, so you kind of walk away from them because you don't know what they're going to do next. And so unstable is high energy. And if you're going to be high energy, you're not going to exist in that state very long. So what happens is this electron is going to emit, give off energy, and then jump back eventually to its ground state position. In order to jump back, it has to release the higher energy. The reason why it can exist farther away is its higher energy, okay? So it emits the extra energy it gained, okay, the exact amount. That's what's cool about all of this. And it jumps back to its ground state. But what's really cool is the energy it gives off is the form of electromagnetic radiation. And most of the time, it's in the colored or visible spectrum. At least in this course, we talk about it. So given the type of energy it is, and of course, the details of this isn't that important, but what you need to know is that it can give off different forms of light in different colors. You may have learned that the blue and the indigo region has higher frequency, which means it has higher energy, which means it'll be a bigger leap. And then if you're in the red or yellow region, the frequency of the electromagnetic radiation, is lower, so the energy is lower, and that would mean it's a shorter leap. It doesn't really matter here. The bottom line is they said to you, explain in terms of electron how it emits colored light. Well, light is energy, and if it's going to emit energy, it has to return to a lower energy state. We're going from an unstable to stable. And if you think with me, party people, this parallels a lot of things in your class. For instance, think with me for a second, heating and cooling curves. If a gas becomes a liquid and eventually a solid, you need to understand, in a cooling or heating curve, I'll just draw it as a heating curve, as most of the time you see it this way. Here's the gas phase, here's the liquid, and here's the solid. You should know to go from a gas to a liquid to a solid, you're giving off your extra energy because gases have tremendous energy. Gases are more unstable than solids. Solids are in regular repeating geometric structures. Gases fly around the room. So a gas become a liquid or a solid, it's got to give up its extra energy. It's going to go from that unstable state to a stable state. Okay, that's important. So if we're in this unstable high energy state that feels the nucleus less because we gained energy, it's going to quickly jump back and lose that extra energy and emit light. And that's the answer, party people, is that when a strontium electron in an excited state, it's going to move to a lower energy state and then emit the extra energy as light. So let's go to the booklet and understand that different elements have different number of protons and electrons, and these distances will be unique for each element. So the type of leap back will have a different amount of energy and then give off different light. That's why different elements have different light given off. And the type of light that's given off is unique. That footprint of the individual light patterns that these guys give off can be used to identify them. That's actually the next question. But let's go on to 73 and answer that in the booklet. So in number 73, energy is emitted in the form of light, if you want to say, when electrons in higher electron shells move to lower electron shells. And you could say energy is emitted when electrons in higher energy shells. I could say energy here. Okay, clearly I could say higher energy, which by the way is what? More unstable, move to lower electron shells, or what? More stable cells. Okay, so lower energy shells. I've seen part 2 questions where they wanted you to talk in terms of the energy. Okay, so again, the shells that are farther away are higher energy. Shells that are closer are lower energy. To go to low to high, you need energy. So 72 was about moving away from low to high, so you needed energy. 73 was about going from what? high energy to lower energy, which means you have to emit the extra energy you had to get to the lower energy position. And this energy is in the form of light. Sometimes you'll hear the word photons. And again, that light is specific for the type of element based upon these distances, these transitions. Number 74. So in number 74, state how bright line spectra, and then that, by the way, is just another fancy way of saying light viewed through a spectroscope. And don't get crazy with that. That's just a device that helps take the light emitted from atoms that were excited. That means they did what? They jumped farther away to a higher energy orbital or orbit, higher energy, HE, this is low energy. And then because they were excited, had energy, and they pulled away from the positive nucleus, they very quickly jump back to their ground position. And to go to lower energy, they release light. Remember, you absorb energy to jump away, and you release light by when you jump back. Now, this light that gives off has unique wavelengths, okay, or unique light based upon how far the electrons jump. Individual atoms have different number of protons. We know the proton number identifies elements, and they have different electron arrangements because they have different number of electrons. So the transitions for these electrons will be very different for every individual atom. So the question states, state how the light given off, viewed through a measurement device that can look at the light that's given off when electrons jump back, can be used to identify metal ions in the salts used for the flame tests. The bottom line is different elements have different lights given off because they have different number of electrons, different number of protons. These transitions, okay, the distance electrons do when they jump back are bigger or smaller. They give off different types of light. If you were able and lucky enough to have the demonstration done for you where your teacher may have used these gas tubes, okay, and use diffracting lens for your eye, you're able to see these bright line patterns. And bright line patterns just represent the actual different wavelengths by the different leaps that electrons can make. So electrons that exist, let's say, let's put electrons all in these four energy shells. So I can have an electron that jumps from here to here when it's given energy, and that's why the this box you saw was plugged in, and you had these gas tubes, and electricity was given to excite the electrons, but then they jump back. Sometimes they can jump back to a shorter position, and that's lower energy, and that would give light more in the red region. Sometimes it could jump back farther, and that would be a shorter wavelength with higher energy light that could be, let's say, in the blue region. So because atoms again have different arrangements and different distances based upon the different number of protons, and all of that really isn't that important, they're going to have unique lines, bright lines, and these bright lines represent the different leaps that these electrons can make in this particular atom. So why are there different types of light, okay, by the different salts? Okay, so the answer really lies in the fact that different elements have different unique colors given off when they are excited and return to their ground state. So the question states, how can they be used to identify the metal ions in the flame test? Well, basically you can take the known light that's given off by these particular elements or salts and then compare them. That's very simple. So knowing the light that these guys give off when they're pure, if you have an unknown, you can just match the type of light with the standard. All right, so let's go to the answer booklet. So 74, I say the spectral lines are compared to known bright line spectrum. That's how you figure out what element something is. Okay, so we discovered helium on the sun, which we didn't actually go to before we discovered it on the earth. The sun gives off light. We took that light, put it through a diffracting gradient, and we got the different bright line spectra that represents the different type of wavelengths of light. Okay, and we compared this bright line spectra with the known elements of the day, and we basically identified all the known elements that are burning in the sun except for one group of lines. And one group of lines they said must have been from an element we haven't discovered yet, and they called it helium, the god of the sun. And lo and behold, years later, we discovered a new gas that was basically um, boiled off from a group of gases, or condensed, however you want to think about it, and they ran it through a bright line spectrum, which means they heated the sample, excited the electrons. When it jumped back, it gave off the same lines that they found in the sun, and pretty cool stuff. So basically, you're comparing known bright line spectrum of elements, okay, to the unknowns. So the spectral lines observed are just compared to the known. And of course, you could say this so many different ways. Find the element that emits light with the same wavelengths that are observed. Okay, the spectra from the flame test are matched with two of the lines on the chart if you have one, and compare the spectral wavelengths to those of known elements. Remember, these bright lines represent certain wavelengths. Longer wavelengths are for the red, just shorter wavelengths are for the blue. Remember, the different colors really represent different energies and different distances. Okay, number 75. Number 75, and it has a new blurb, and it's about unique odors and flavors of many fruits, primarily due to small quantities of a certain class of organic compounds. The equation below represents the production of these compounds. And again, like I've been telling you, this little blurb may have nothing to do with exactly what these questions are about. It may just, again, be very much paralleling what these questions are, kind of supporting them. Sometimes you can go back into them. So if I just read the question, show a numerical setup. They just want the setup. They don't care about the answer. We're calculating the gram formula mass for reactant 1. So there's reactant 1. They want the mass, okay, for the formula, right? The mass for the formula. So what do we have here? We have two carbons, C2. We have 1, 2, 3, 4, 5, 6, H6, and 1 oxygen. And it's so C2H6. So what we're going to have to do is try to find the grams per 1 mole. And to do this, all we're going to do is basically add up the atomic masses of each of the different elements. However, there's 2 of the carbons and 6 of the H's and 1 of the oxygens. And that's all they're doing in a gram formula mass. Now, we would normally do this gram formula mass to find the grams per mole, or if we're doing a conversion from mole into gram or from grams into moles, you would need this converting factor. So you've done this a lot in this course, I'm sure, but they just want the setup. So let's go to the booklet and do that. So in number 75, our molecular formula is C2H6O. Okay, it's the exact arrangement of atoms in reactant 1. To find the gram formula mass, we're going to need 2 carbons, okay, and it's going to be 2 times the actual gram atomic mass, okay. And so what is that number? So we go to the periodic table, and there we have the gram atomic, I would say the atomic mass of the element to be 12.011. You can use that entire number, or you can just round to the whole number. And when you do that, what you're really doing is getting the most common isotope. That's right. Remember, this decimal place is here because you're averaging the other isotopes, the other forms of carbon that also have 6 protons but a different number of neutrons. So in any case, that's the reason why you can do that. So carbon is going to be 12. Oxygen rounds to 16. You can use this number if you like. And then hydrogen, all the way up to the left, they put it here even though it's a non-metal because it has 1 valence electron, is of course 1.0794. I'm going to round it to 1. Either way, you could do that. So back to the booklet. So the atomic mass of carbon was 12. So 2 times 12 is 24. Now they only wanted the work, okay? So there's many ways you can do this, but I'm going to show you how you would do it if you forgot. And then of course we have 6 hydrogens. 6 times 1 is 1. Okay, well, where am I get this 1 from? This is from the what? From the periodic table. The atomic mass of hydrogen is 1, 6 times 1. And then we have 1 oxygen. So 1 times the atomic mass of oxygen in the periodic table, its atomic mass is 16. And essentially, you're adding these together, okay? So if we wanted to solve for it, we certainly could and have fun with it. 6 and 4 is 10 and 16. And then you would get 46, and the unit is grams per mole. And if you went as far as this, you wouldn't get any extra wrong. But really, all you needed to know was 2 times 12 plus 6 times 1 plus 1 times 16, or something like that is all you needed, okay? And if you went farther to answer the entire question, that's fine, because they were just looking for the work, okay? And essentially, the work is in there, all right? And this is another example, or anything mathematically. Instead of 6 times 1, you put 6. Instead of 16 times 1, you have 16. That would have been fine just as well. You could have just said 24 plus 6 plus 6 is also the work. So many ways to do that. You could have also used the atomic masses here that I got from the periodic table. You could have used the actual numbers as well. It wouldn't make any difference. So that's just the work. Number 76. Okay, so in number 76, explain in terms of molecular polarity why reactant 2 is soluble. Okay, now it's very important when you solve for these problems that you answer in terms of what they are asking for. So in this case, they're asking for molecular polarity. And it's really important because when you talk about solubility, solubility is the idea that like dissolves like. Now, what does that mean? You probably heard of that. What does like dissolves like mean? Well, it means that if something is polar, it'll dissolve in something that is also polar. That's why water loves to dissolve things that have positive negative ends, even positive negative ions. And things that are nonpolar, like fats and oil, dissolve other things that are fats and oil. And it's the reason why things that are nonpolar do not dissolve in things that are polar. So why is reactant 2 soluble? Now it's soluble, let me finish this out here. It's soluble in water, and we should know water is polar, because this molecule is polar. It's just that simple. And why is it polar? When you look at its shape, it's very asymmetrical, okay? And definitely is going to have, these oxygens are going to have high regions of electrons. So this asymmetricality, or this asymmetrical molecules, have an unequal distribution of electrons. But in terms of molecular polarity, we would say that reactant 2 is soluble because it's polar, and it will dissolve in polar water because like dissolves like. It's that simple. Let's go to the booklet. So in number 76, both molecules are polar. Now you certainly could say both water molecules and the acid have polar molecules, like dissolves like, polar dissolves polar. Okay, reacting 2 molecules in the water molecules have similar polarities. Many ways to say the same thing. So easy for me to say. So moving on to 77. Number 77. State the class of organic compounds to which the product 1 belongs. So product 1 is a compound that has a functional group, and functional groups have a unique arrangement of atoms that drives their properties. Structure is king, and if the structures are similar, they'll have similar properties. Now there's 2 ways we can answer this. The first one is we should know from table R what this compound is. Now, what is this compound? Well, you have this functional group, okay, and then you're going to have some, basically you're going to have some other places of the functional group, which is the rest of the organic molecule. So if I redraw this, what I have here, and let's make some space. So what I have here, party people, is I have this C double bonded to an O, bonded to an O, then it's bonded to the rest of an organic molecule, and then it's bonded to another rest of an organic molecule. So we're looking for that functional group. It's a middle group. This, notice the color here, is the rest of the molecule. So let's go to table R. So table R is talking about the different types of functional groups, which is basically different arrangements of atoms. And if those arrangements of different atoms on a hydrocarbon are similar, then the properties are similar and they're a different class of compound. Notice the word was class of compound. So table R is where to look. So we're looking for a middle group in between R's, and we're looking for a carbon double bonded to an O, to a single bonded O, to a rest of another organic molecule. So when I look carefully, I'm looking for a C double bonded to an O and a carbon double bonded to an O, all right, that is bonded to another organic compound. Now, the two that I chose are very similar. Let's look at them carefully. Carbon double bond to an O, to an O, to an H. That's a COOHN. That's a Cu group. And this is a carbon double bond to an O, to an O, to an R. Now, what's the difference? Let's go back to our problem. Okay, let's go back to the original worksheet to see which one this is closest to. Looks very similar. So notice the carbon double bond to the O, and the O is in the middle. But notice this H is bonded directly to a carbon, not to an O. So there's not a COOH ending. This O is in the middle of the compound, and you have a carbon double bond to an O, and this is just the rest. So this is not the acid. So look at this, carbon double bond to an O, and that O is in the middle. Okay, it's not, this is not at the end. If it was, it'd be that organic acid. Let's go back to table R again. Remember that carbon is double bonded to an O, and then the O is in the middle of a compound, not at the H end. So carbon double bond to the O, and the O is in the middle of the compound, not with the H at the end. So if there's an O at the H at the end, that'd be an organic acid. So since we have an H on this ending, and this is the rest of an organic molecule, it's an ester. Hope you can see that carbon double bond to the O, and the O is pointed inside the compound. And the O is pointed inside the compound. So this is an ester. And that's what you would put for number 77. Now, something else to think about. You should know that esters are aromatic. They make unique odors and flavors. So I said there was a second way you could have done this. And you should know that this is an example of esterification. Alcohol, an OH group from table R, and organic acid makes esters in water. And you should know that esters have unique odors. They're the fruity smells of nature. Okay, so that's something else you could have recognized. You could have recognized this to be esterification. They could ask you this, what kind of reaction is this? And it's a condensation reaction or a dehydration reaction. Water is coming out as these guys come together and bond. Okay, so very important. And you could also have known that the aromatic organic functional groups or class of compounds are your esters. So a couple of different ways to do this. Probably the best way is to go to table R and see which one you have. And using table R, understand what is a middle group, what's an ending group, and this is clearly a middle group. Okay, and that would have helped you do that. Let's go to the answer booklet. So number 77 is ester or esters. Okay, and it's right from table R. Number 78. So number 78, state the purpose of the salt bridge in the voltaic cell. Voltaic cell, Alessandro Volta, okay, was the first person to make a battery. And so this is a list of materials to make a battery. Okay, so voltaic cell, you have to know, is the battery. And they want to know the purpose of the salt bridge. Okay, so we have some materials here. Okay, well, if you remember, a battery is when we have two half cells. Okay, we're going to separate the reduction, the oxidation, and we're going to put in our two metals. One metal is going to be better at oxidizing than the other. We're going to separate them by a conducting wire. They're going to be in a solution. Okay, so what do we have here? We have a strip of zinc. We'll make this zinc, Zn. We'll make this copper, Cu. And essentially, electrons will flow from anode to cathode, and whoever's better at oxidizing will be there. But what this question is about the salt bridge. Why do we have a salt bridge in a battery? Well, the salt bridge allows only ions to flow, and that certainly could be the answer. But why do we have one? Well, okay, if you look at zinc and copper, and those are the two metals, who is better at oxidizing? Well, if you go to table J, you will see that zinc is higher than copper. You'll see H2 written here. Okay, lead and then eventually you get to zinc. Zinc is much higher, and this is an activation series, or this tells an activity series. Zinc is more active. And what do metals do? Metals lose electrons. You're saying, but why am I doing all of this for the salt bridge question if I know it? Because I want you to understand the one who's better at oxidizing is going to be your anode, okay? And so what's going to happen here is the zinc is the anode, and this is the cathode, which is the copper. Electrons flow from the anode to the cathode. Why? Well, anox, oxidation occurs. So zinc is going to become zinc plus 2 here. And then it's going to send 2 electrons to the cathode. In the solution, we already have copper plus 2. It's going to get reduced by gaining gaining electrons is what? Reduction. It's going to gain negatives. It's going to become pure copper, and it's going to get plated. So this is going to get bigger as this one gets smaller. But why the salt bridge? Very important. The salt bridge is there because it already has ions in it. Let's make it sodium is in here, sodium plus, and Cl negative. Now over time, as the zinc oxidizes and makes more zinc plus 2, electrons have a tough time leaving if this beaker gets more positive. So we need something that's negative in the salt bridge to move down to counterbalance the increase in positive. We can't let this beaker get positive. So the negative ion moves down. And over here, we're losing copper plus 2 every time it pulls the 2 electrons or gains the 2 electrons that are sent to it from the anode. So this beaker is losing positive. So it's going to get negative. So the positive ion in the salt bridge migrates down to counterbalance the loss of the positive. So the purpose of the salt bridge is to maintain electrical neutrality in these beakers so electrons can flow. Only ions flow. You certainly could also state that allows the ions to flow. Both of those are acceptable. And I went through all of this so you can understand how this works, because sometimes, and they may ask, what ions will flow. Okay, so the purpose of the salt bridge is to maintain electrical neutrality so that these beakers don't get positive or negative so electrons can flow. And it also allows for ions to flow. So in number 78, electrical neutrality of the solutions is maintained, or it allows the ions to flow. No electrons, right? This has nothing to do with electrons moving, okay? That has to go from metal to metal, from electrode to electrode. Number 79. In number 79, complete and balance the half reaction in your answer booklet. You don't do it here in your answer booklet for the oxidation. What's oxidation, Leo? The line says losing electrons is oxidation. And notice they give you zinc. Now, when we went over 78, we said that zinc is better at oxidizing than copper, so it's the anode. How do I know? Because of anox. Okay, so let's do that. So in number 79, we got zinc, and what does it become when it oxidizes? How do I know what it becomes? Well, when it oxidizes, and again, oxidation, Leo, the lion, says you're losing electrons. Hello, this is a standalone metal. What do metals do? Metals lose electrons because they hold on to them very loosely. They have low attraction. That's why they're the big atoms. A really, really important point in this course. So they're going to become a positive ion. All metals become positive ions. So if you're not sure what ion it becomes, let's go to the periodic table. And let's do that now. So here's zinc. It's written as an atom, which is neutral. I say atom, you say neutral. Atom, neutral. So therefore, this is a charge it likes to become. Hey, these are all metals. And how do we know? Well, we have this staircase here, right? This is a staircase. And anything left of the staircase is your metals. And all metals become positive ions. You can't find me a metal that's left of the staircase that becomes negatively charged. All metal atoms, neutral, okay, become positive ions. And zinc is no different. It becomes +2. So that's the charge it becomes when it gets oxidized. When the atom loses 2 electrons, Leo, it becomes +2. So zinc becomes zinc +2. Now, when we balance a half reaction or balance any reaction, we balance the mass, one zinc, but the charge. Remember, standalones are 0. This side is +2. So we have to add the electrons. How many electrons do we add so that both sides have the same charge? Well, zinc is 0, and I have to add something here. I'm going to add 2 electrons. And a -2. Each electron's -1, -2, and a +2 is 0. And that is a correctly written half reaction for the oxidation. Notice the electrons are on the what? They're on the product side. That means we're producing electrons. Or the electrons are on the what? The right side of the arrow. They're leaving. Just like if I had A plus B making AB, and I wrote heat here, or the test writers wrote heat here. Heat is after the arrow, it's exiting, right? It's in the product side, and we would call this exothermic. Okay, because the heat is in the product side. We're producing it. Electrons are in the product side. We're producing or releasing electrons, or we're losing electrons. Okay, number 80. In number 80, compare the activities of the two metals. Okay, I wish they would have said reactivities, but that's what they're talking about for constructing the voltaic cell. As I talked about number 78, zinc and copper, for this to work, zinc and copper have two different abilities to lose electrons. The one who is better at losing electrons, again, losing electrons is oxidation, and anox, that's where the anode is. So we start this always when we do a voltaic cell problem by looking at the two electrodes and seeing which one is better at oxidizing. So to see which one is more active as a metal, and what do metals do? Metals lose electrons, and when they do so, they oxidize and become positive ions. Who's better at doing this? Well, there's a table, table J. Let's go see. So notice table J is the activity series, and the most active metals are on top. They have the greatest ability to be like a metal, which means lose their electrons and oxidize. So lithium is the best at it. Now, scrolling down is zinc higher than copper. And of course, there's zinc, and there comes copper. So zinc is higher on the list of the activity level of metals. And since metals lose electrons, zinc is better at losing electrons or oxidizing than copper. And that's why they use copper pipes in your house, because they do not want the water to corrode the metal pipe, and therefore if you did so, you'd have a huge leak at some point, as the water would corrode a lot of different metals, or the ions in the water could do so. Copper is less susceptible to rusting because it doesn't oxidize or lose electrons very well. Look who's on the bottom. Why does gold stay shiny? Because it refuses to oxidize under normal conditions. There are some chemicals that could force it to, but they're not natural. That's why gold is used for electrical contacts and or jewelry, because it stays shiny. Okay, so zinc is higher than copper on table J. Now notice also, as a fun aside, nonmetals are listed. Now nonmetals love to gain electrons. They like to get reduced. They gain electrons. This is showing the ones who best get reduced. Okay, so the one who gets reduced is on top, okay, of the one who gets oxidized. Here, metals are good at oxidizing. It's higher than the one who gets reduced. So number 80, I say zinc is more active than copper. You could say zinc is higher than copper in table J. You can say zinc oxidizes more readily than copper. So many ways to say that, but table J was your friend there. Number 81. So number 81, identify one item of the laboratory equipment required to build an electrolytic cell. That's different. Okay, so identify one item that is not included in the list. So electrolytic cell is totally different from a voltaic cell. A voltaic cell is a battery, meaning chemicals are set up in such a way that a spontaneous reaction occurs that produces electricity, okay, from chemical energy. Okay, so from chemical energy, we make electrical energy. Okay, and electrolytic cell, if as the word implies, you're using electrical energy to make chemical reactions go, because why? These reactions are not spontaneous. They don't happen very well. So we're going to need a power source to force them. So in 81, you need a battery or an external source of energy. Okay, many ways to say that, but essentially for an electrolytic cell, this is where you have electroplating or electrolysis of a fused salt. You are trying to make a reaction go that normally doesn't go. Think of a battery that runs your phone. When it dies, you plug it in to make the reverse reactions occur that normally wouldn't go, but because of the energy, you're making it go in the reverse. Batteries, in this type of battery, the anode gets smaller. But what if I make the zinc plus 2 go backwards? We force what normally doesn't happen by giving it energy. So when you plug in your phone into an external energy source, you're basically making a electrolytic cell occur, and you need electrical energy. Okay, but the bottom line is you need a power source to make it happen. A battery doesn't need a power source. It is the power source. A battery doesn't need a battery to run a battery to run a battery. You get the point. Okay, so this is exothermic. Electrolytic cells are endothermic. They require an energy source. So an 81 is a battery. Certainly could say external power source, source of electricity, all the above. Number 80. So in 82, we have between 82 through 85, we've got this little blurb here. I'm going to go right to the question. Oftentimes the question that goes with this information doesn't use this information. Let's see if that's the case. Identify the highly penetrating radioactive emission that exposed the photographic plates. Well, we don't know that off the top of our heads, so we go back to the reading, and they said that Antoine H. Becquerel discovered that uranium could expose a photographic plate wrapped in heavy paper in the absence of light. It is shown that the uranium compound was spontaneously releasing particles and high energy radiation. Okay. Further tests show the emissions from the uranium that exposed the photographic plate were not deflected by charged plates. That means whatever that type of emission was, if you had a positively charged field and you had a negatively charged field, that this would not be attracted. It would go right through. So what type of radioactive emission does not have a charge? Okay, and by the way, it's highly penetrating. So let's go to table O to review all the different types of particles that we have in this course. So here we have table O, as we can say it, okay, in places of Long Island. Okay, so table O is here, and here are all our particles. Now a beta particle is really an electron, and to understand this is the mass number, and this is the charge number. And things you should know is this. If a particle, like an alpha particle, comes from elements that are unstable because they have too many protons, they'll lower their proton number, right? Every element beyond atomic number 83 is radioactive because of that. So this is a really, really heavy particle compared to the others. So therefore it moves slower, and it's less penetrating power, and it has a positive 2. Beta particles, which are essentially electrons that come out of the nucleus, okay, when you have essentially too many neutrons in your nucleus, a neutron becomes a proton. But in any case, they're showing a mass of 0, and that's not really true. It's just that an electron is 2,000 times lighter than a proton, so this is really an insignificant number, so they put it to 0 and has a charge of -1. Now beta particles are a lot more penetrating. They're a lot more dangerous than alpha particles. Your skin or a piece of paper will stop alpha particle radiation, but not beta. And the reason is betas, of course, are lighter, but they will be deflected by a charge, right? They're -1, so they'll move toward a positive plate. These guys are +2 because of the 2 protons. They'll move toward the negative. If you look at our other choices, the only thing here that has no charge is gamma radiation and neutrons. Now, neutrons is not a radioactive emission. We just don't emit neutrons. They do happen because of maybe fission or other types of artificial transmutation, but they want high penetrating ability. Gamma radiation is the most dangerous. It has absolutely no mass. Even though beta particles, they put as 0, which is an electron, it does have some mass. This absolutely has no mass because it's essentially high energy light. Okay, so it's not, doesn't really have any matter, and it has no charge. So having no charge and no mass, this is the most penetrating, and it would go right through a electromagnetic field. So in 82, we write gamma radiation. So really it was a question of could you identify a highly penetrating particle that would not be attracted to a positive or negative field, so it would not have any charge. And it's highly penetrating because it has no mass. So gamma radiation is what we were looking for, or gamma, all good. Number 83. In number 83, complete the nuclear equation in your answer booklet for the alpha decay of uranium-238. Okay, so we're going to go to our booklet and we're going to basically complete it. Now, always understand that you may need table N and or table O to help you identify the particle and what type of radiation it gives off. Now, they're telling you it's alpha decay, so we don't have to look that up, but they could have said, complete the nuclear equation in your answer booklet for the decay or the natural transmutation of uranium-238, and you'd have to go to table N to see that it undergoes that type of decay. Or they could ask for what kind of decay does uranium-238 have, and table N tells you that. So let's go to the booklet. So they set this up very nicely for us. Sometimes they would just give us uranium-238-92 and fill out the rest of these two particles. Again, if you didn't know it gives off this alpha particle, table N, okay, would tell you that. All right. But in this case, we just want the final particle. What's the product of something called natural transmutation? So how this works is very simple. 238 is the mass number of this isotope of uranium that's radioactive, and it's naturally transmutates because what does it do? By itself, it gives off a helium nucleus. That's why they put He here, 4/2, and this is called an alpha particle with two what? Protons and two neutrons. And if you didn't know that this is an alpha particle, table O would tell you that. Now, here's the question. What is the final product? Well, we know all the numbers on top. 238 equals 4 plus what? Well, 4. What number plus 4 is 238 is 234. And then what number plus 2 is 92? And that is 90. And so you would put 234 here, 90 on the bottom, and you would have to put in the correct chemical symbol. Do not put uranium, as most people would do. That, of course, is wrong, because the atomic number for uranium is 92 protons only. This proton number changed because it lost 2 protons with 2 neutrons. Why? Because it has greater than 83 protons. It's too many protons. That's the reason why it's unstable. So we've got to go find what element that is. Let's go to the periodic table. So atomic number 90 is Th, or thorium. And if you don't like that, you go to table S and it tells you that Th is thorium. Okay, so let's go back to the booklet. And we put Th here. And that's how you finish the problem. So all it is seeing these numbers on top on one side have to add together to these numbers. Okay, think of equal signs happening on the arrows. You could have also just placed, say, hey, I have thorium-234. Remember, these are isotopes. By just putting Th and 234, you're just mentioning or talking about a particular isotope of thorium. Okay, you don't need the 90, it's kind of redundant, but you have to have thorium. Any uranium here is wrong. Okay, number 84. So number 84, determine the number of neutrons. Do we even need any of this information up here? No, read the question first. So uranium-233, how do we do that? Well, uranium-233, what is the atomic number for uranium? It's 92. And we should know that the protons and neutrons are up here, and this is the proton number. So when we subtract 233 and 92, okay, we are going to get 141. Very simple. I know you needed to see it in the answer booklet. There it is, number 85. Number 85. Identify the type of nuclear reaction that occurs when an alpha or beta particle is spontaneously emitted by a radioactive isotope. So here's a great example, carbon-14. We usually date living or past living things with this radioisotope. This is a isotope of carbon that loves to give off beta particles because it's unstable. So it gives off this beta particle. Really what's happening is a neutron in the nucleus basically gives off a negative charge and it becomes a proton. You lose your negative, become positive. So what number plus -1 is 6? That'd be 7. Atomic number 7 is nitrogen. What number plus 0 is 14? 14. And look here, we've made a neutral compound. So this is an example of beta particle or beta decay, but what I want you to understand is when you have one element by itself, in this case one radioisotope, okay, emitting one particle that gets more stable because its nucleus is unstable for a couple of different reasons, too many protons, too many neutrons, too less neutrons, all of that isn't that important, but having one reactant means that this is natural transmutation. You could also call it nuclear decay, radioactive decay, natural transmutation. All of that's the best. I think the best one is natural transmutation. What I could not accept is artificial. Artificial would be if we had this colliding with something else, if there was two things in the reactant side. So the answer is natural transmutation. They'd accept decay, radioactive decay, nuclear decay, natural transmutation. They really wanted to give you the answer here. I mean, 84, 85, they were, in my opinion, I can't speak at this point of the test, they were trying to get you some points here. This stuff you should be saying thank you very much. Okay, and thank you very much for listening. Good luck.